Bismillahirrahmanirrahim. Assalamu alaikum dear students. We are now starting the lectures for the 6th week for this semester. So this one is actually first lecture for the 6th week of wireless and mobile communications. So before starting, let me quickly review what we have discussed in our last lecture. Actually, we started the topic of path loss modeling, and we discussed that path loss modeling is actually a critical parameter in designing any system, because it is used to predict how the signal would be received at the receiver side. So whenever we are trying to model a path loss between transmitter and receiver, we generally try to relate the received power with the transmitted power. In fact, this modeling is needed for outload propagation as well as indoor propagation. Because of the nature of difference of environment in indoor and outdoor, generally there are different models which are used for outdoor propagation and indoor propagation. So we'll talk about those models in this presentations in this week, inshallah. Last week we started a discussion on mathematical modeling for path loss, and we started to have discussion on free space propagation model. We noticed that the received power in free space propagation model is related to the square of the distance between transmitter and receiver. So if we increase the distance between transmitter and receiver, the received power gets reduced. We also took some examples related to this free space propagation modeling. Then we started the discussion on two-ray or also called ground reflection model. Free space model is generally used for open environments only. So most of the practical environments they differ from the free space behavior. So a relatively better model is actually two-ray ground reflection model, for which we started discussion, and we obtained some mathematical results related to two-ray ground reflection model. So we would continue the topic in this lecture. So before starting the further discussion on two-ray ground reflection model, let me quickly review what we have discussed in the previous lecture. So this is the graphical illustration for two-ray ground reflection model. We have a transmitter here and we have a receiver here. So we assume that two rays they are received at the receiver side. So basically the electromagnetic wave which is being transmitted from the transmitter and is received at the receiver side is represented by two different rays. First ray, which is representing the line of sight component, is the one which goes directly from the transmitter to the receiver. So we are representing the field strength with this line of sight component with this ELOS. The second ray, which is received at the receiver, is actually received through a reflection from the ground at certain place. So a ray emitting from the transmitter goes towards ground, hits the ground at certain point and gets reflected back to the space, and that reflected ray ER is received at the receiver. So at the receiver side, the total electric field is actually sum of two components. One is line of sight component and second is the ground reflected components. The notation that we used in this geometry was that we are using HT for height of transmitter, HR to represent the height of receiver, D is actually representing the distance between transmitter and receiver, or simply it is transmitter receiver separation. E naught is the free space E field. Delta is actually path difference between two different rays. So we have this ray which is represented by ELOS, and the other ray which is actually ground refracted ray which goes from here to here. So this one, there is a difference between the path, the propagation path between these two rays, and this difference between these two rays, path difference, is approximated as 2hthr upon d, which we have calculated in our last lecture. Secondly, because the rays are taking different paths, so when they receive at the receiver side, they will be received with different phases. So both the rays would have a certain phase difference between them, and that phase difference was also calculated in our last lecture, and that can be approximated as theta delta is equal to 4 pi hthr over lambda d. So with these calculations, we tried to estimate the magnitude of the received E field at the receiver side. So this total E field at the receiver is actually sum of two components, which is line of sight component and the ground reflected component, and that the total E field is it can be represented as 2 E naught d naught upon d sine theta delta upon 2, where theta delta is this path difference, d naught is the reference distance, E naught is the E field at the reference distance, and d is actually the TR separation as indicated here. So we continue our discussion from this point. For most of the practical scenarios, we have a certain condition. Typically assume that if we are in an urban environment, you can see that the transmitters, they have a certain height which is up to a certain meters of length. For example, a typical height you can take as 40 meters or 50 meters maybe. Receiver, in most cases receiver height is same as the human height, because most of the mobile receivers, they are intended for human use. So generally these receivers, they are the receiver height is relatively very close to the height of human, so which is you can take it as 1.5 to 2 meters maybe. This d is actually the propagation distance between transmitter and receiver, and this distance, because each of the cell coverage area of a base station that has a radius of kilometers of length, so this d is of the orders of kilometers. So you can see that the transmitter antenna height, receiver antenna height, in most of the practical cases is actually they are very small as compared to the separation between this transmitter and receiver. So if we have this scenario that where the distance between transmitter and receiver is significantly larger as compared to the receiver antenna height and transmitter antenna height, so we can make further approximations in this expression that we have obtained in last week. First thing, you should note that if d is large, in that case the theta delta would be much smaller, because this theta delta is actually related to this path difference, and if d gets larger, so this path difference would get smaller. So if you can see that if they are separated, so these two rays would become closer to each other, eventually the path difference would get reduced. So relevant this phase difference would also get reduced. So what I want to explain is that for most of the practical cases, this theta delta is actually a small value, and with having this small value of theta delta, we can further approximate the expression that we have obtained last week. So for the case where this TR separation is greater than the height of transmitter and receiver antenna, typically we represent this relationship mathematically by this value, that if d is much greater than under root of HTHR, in that case this theta delta is a small number, and for example, if theta delta is smaller, such that theta delta by 2 is smaller than 0.3 radians. So in that case, the sine function which we have represented in the previous expression, this sine function can be approximated further, because we know that when angle is small, in that case sine x is actually approximately equal to x. So sine x would be same as x for the small values of angle. In that case, if theta delta by 2 is much smaller than 0.3, we can approximate sine theta delta by 2 to be equal to theta delta by 2. So the angle, the sine of the angle would become approximately equal to the angle itself. And we have already calculated theta delta, which is represented here, that theta delta is 4 pi ht hr upon lambda d. If we substitute that value of 4 pi ht hr over lambda d, so we can approximate this sine theta delta by 2 to be 2 pi ht hr upon lambda d. So if you substitute this value in the previous relationship which is given here, so we will see that this total electric field can be represented in terms of the heights of transmitter and receive antennas. This 2 epsilon 2 E naught D naught upon D is the previous value, and sine theta delta by 2 can be replaced by this expression. So we get this value, and you can see that for a specific type of environment, all these parameters, they are constants. E naught, D naught, pi, ht, hr and lambda, they are generally constant for a specific type of environment. In that case, we can collect all those constants in a constant value represented as k. So this k is a constant number which is actually dependent on the field strength as well as the antenna heights and the wavelength. So in that case, total E field is actually represented as k upon d square, or in other words, the E field is actually inversely proportional to square of the distance. After getting the approximate expression for this E field, we need to calculate the received power, because if you recall, for the path loss modeling, we are generally interested in calculating the received power rather than having the value of electric field. So if we want to calculate the received power at the receiver side, in that case we can use the previously derived relationships. If you recall our lecture number 14 in the 5th week, we discussed the relationship between E field and the received power. If we use those relationships directly, I'm not going to do that here, but you can refer back to the lecture number 14 where we have derived that relationship, and by using that relationship we can convert this received electric field E total into the received power PRD, and in that case this PRD is given by PT GT GR upon HT square HR square upon D raised to power 4. So this is the received power when we are using the ground deflection model, and you can see that for ground deflection model, this received power is actually related to the fourth power of the distance. So this received power falls off with fourth power of the distance. Alternatively, we can say that the received power is actually inversely proportional to the fourth power of the distance. If you compare this result with the one that we obtained for free space, and you must recall that the free space, the received power is actually inversely proportional to d square, and here we have received power which is inversely proportional to the d raised to power 4. So for this particular case, the received power is decaying at a rapidly fast rate as compared to the free space path. And of course, if there are obstructions and other buildings which are obstructing the propagation, in that case we would expect more loss, which is represented here as well with the high path loss index value. Second thing you must note here, that this received power for the large value of d that we have obtained here, this received power is actually independent of the frequency. So if we change the received power frequency, we would not get a significant change in the received power. So this is another important observation related to this result, that this power is this received power is independent of the frequency of operation of the electromagnetic wave. As we discussed previously, that for most cases the path loss is generally represented in decibel values rather than representing in fractional value, although we have this fractional results, but we can use the same result to represent the path loss in dBs. So if you want to convert this into dB, you can simply take 10 log on both sides and then represent the path loss. If you simplify that expression, you would see that the path loss in dB for two-ray ground reflection model is represented by this expression here. So this path loss is dependent on D, which is GT, GR, HT and HR. Second important thing is that we have used another alternate expression in free space model as well. Similar expression can be used for two-ray ground reflection model, because the two-ray ground reflection model we have the dependence of power to the fourth power of distance. So if we know the power at a reference distance d naught, we can use that result to calculate power at any other distance. So if P naught is representing the power at d naught, in that case the received power at a distance d would be given by this expression, which is P naught d naught by d raised to power 4. This 4, as we have already discussed previously, that this 4 is named as path loss index, and hence we can say that the path loss index for two-ray model is actually n is equal to 4. So this is the received power related to the two-ray ground reflection model, and we have also discussed that what will be the nature of the E field if we use this two-ray ground reflection model. So let us conclude our discussion by taking a simple problem related to this two-ray model. So we have a problem that a mobile is located at a 5 kilometer from the base station. So we are given the transmitter receiver separation distance to be equal to 5 kilometer. The mobile is using a vertical lambda buffer monopole antenna with a gain of 2.55 dB. So the antenna that is being used at the mobile is a monopole quarter wavelength antenna, lambda by 4 antenna, which have the gain of 2.55 dB. The E field at 1 kilometer, so the D naught, the reference distance which is taken here, is actually 1 kilometer, because we are given the value of E field to be equal to value of E field at a distance which is equal to 1 kilometer from the transmitter. So this E field value is measured to be 10⁻³ volt per meter. The carrier frequency which we are using is 900 megahertz, and we want to find the received power for the mobile using two-ray ground reflection model. And you must note that for two-ray ground reflection model, we need to know the heights of transmitter antenna as well as the receive antenna. So transmitting antenna height is given as 50 meters and receiving antenna height is given as 1.5 kilometers. Oh, sorry, 1.5 meters. I'm sorry. So the receive antenna height is 1.5 meters. So this is our given values. We know the frequency, we know the E field at the reference distance, and we know TR separation. From frequency, it is convenient to calculate wavelength, because we are given the quarter wavelength antenna. So in that case, the lambda C over F, lambda which is given as C over F, can be calculated using by dividing this value of C, speed of light, by the operating wavelength. So C is 3 into 10⁸ divided by 900 into 10⁶. So we get wavelength to be equal to 0.333 meters. as is mentioned in the problem, that we are using a quarter wavelength antenna, lambda by 4 antenna, so we can calculate the length of the antenna, which is actually 0.833 meters or 8.3 centimeters. Second thing, you should note that the gain of the receiver antenna is given, which is 2.5 dBs. So we can use this value to convert it into a fractional value or non-dB value. So GR is actually 10 raised to power 2.5 divided by 10, which is 1.8. Because we know the gain of the receive antenna and we also know the operating frequency, so we can use this relationship to estimate the effective aperture of the antenna. If you recall, we have discussed the relationship between antenna gain and the effective aperture, which is also reproduced here. So from this relationship we can calculate the formula for receiver antenna. It should be square here. I'm sorry for a mistake. I'll correct it in the final version. So A is equal to GR raised to R lambda square upon 4 pi. So this would be 1.8 into 0.333 squared over 4 pi. So you would see the receive antenna gain to be equal to 0.16. Would anyone guess the unit of this? Take a second to guess the unit, because this is actually effective area. So actually the unit should be same as the area unit, so I should have mentioned the unit of meter square here. Okay, so now we have effective aperture as well as the gain and the relevant wavelength and all other relevant details which are given in the question. So we can work on the calculation for the received power. So we need to calculate received power, but we note that this power comes from the value of the E field. So before calculating this received power, we must calculate the total electric field. If you go back a few slides, you would see that the total electric field at the receiver when we are using a two-ray ground reflection model is given by this expression here. So you can use the same expression to calculate the total electric field. So received at the receiver side, the received field would be given by this expression, which is reproduced here. So we know all the constants in this expression. So this is 2 is constant, and the rest of the stuff E naught is given in the expression, which is 1 into 10 to the power minus 3. D naught is also given 1 kilometer, pi HTHR upon lambda d square, and all these parameters, they are mentioned here. So simply if I substitute all the values in this expression, you would see that the received field comes out to be 113.1 into 10 to the power minus 6 volt per meter. So this is the received electric field when we are using a two-ray ground reflection model to get the power. But we are not interested in calculating the field as per question. We are interested in calculating the received power, and we have previously discussed the relationship between E field and the received power. If you don't remember, I would request you to refer back to lecture number 14 to see the relationship between received power and the E field. So this received power is actually power density multiplied by effective antenna, which is given by this relationship E magnitude square upon 120 pi AE, or this can also be represented in terms of transmitted power. Although because we know the received power, so we would be needing this expression here to calculate the total received power. So I can write received power to be equal to magnitude of E square upon 120 pi multiplied by AE, and you can see that we have previously calculated E field, which is actually 113.1 into 10 to the power minus 6. So we can substitute that value here, divided by 125, and AE we have also calculated it previously, which is 0.16 meter square. So we can substitute that value here. So if we simplify all this stuff, so you would see that the received power comes out to be 5.4 into 10 raised to the power minus 13 watt. 5.4 into 10 raised to the power minus 13. However, our convention is to represent the received power in dBm or dBW, so it's better to use the same convention. So we can convert the received power what we have received from our calculation into dBm or dBW. So if we convert it into dBm, so that means that we have to divide this received power with the 1 milliwatt, because for dBm value the reference point that we use is 1 milliwatt. So if we simplify this thing, 5.4 into 10 raised to the power minus 13 divided by 1 into 10 raised to the power minus 3, which is 1 milliwatt, and if we simplify this, we will end up with a received power of minus 92.68 dBm. Similarly, if we intend to convert it into dBW, in that case the reference would be 1 watt. So if you have to divide the received power with the 1 watt value, so if we simplify this thing, and you would see that this comes out to be minus 122.68 dBW. So this is how we can calculate the received power by using the two-ray ground reflection model. So we conclude our discussion here, summarizing important points related to two-ray ground reflection model. Let me mention that the first important thing is that the calculation is based on assuming two different rays, first one which is coming directly in a line of sight, and second one which comes from the ground reflection. The important thing to note in the two-ray model is that the received power is dependent on fourth power of the distance. So if we increase the distance, the power would get reduced with fourth power of the distance. So path loss index that we get from the received power calculation is actually n is equal to 4. So this ground deflection model is more suitable for the environments where we have more losses as compared to the free space propagation. Okay, so this concludes a discussion on the two-ray ground deflection model. So let us start a new topic related to another important phenomena, which is diffraction. So another important phenomena related to the propagation of the electromagnetic wave in the environment is related to diffraction. We have already concluded the discussion related to the effect of the ground reflected ray. Now let us see how this diffraction affects the propagation of the wave. Before starting discussion on diffraction, one important concept related to the propagation of electromagnetic wave is Fresnel zones. This Fresnel zone concept. What is the concept of Fresnel zones? Actually, the calculation that we did in the case of ground reflection model was based on the propagation of ray. So we assume that the wave is propagating in the form of a ray, and we made our calculation on the basis of that ray. However, the important parameter here is that the ray is actually not the true representation of the wave. It's an approximation to the wave. Actual propagation is actually done through wave. So wave, whenever you have a transmitter, say for example this part is transmitter here and we have a receiver here. So whenever a wave is transmitted from the transmitter, it spreads in the environment. So there is the entire environment between this transmitter and receiver it's actually filled up with that wave. So not only that rays, the entire region between between this transmitter and receiver is actually affecting the overall propagation. And if there is an obstruction which comes in between, so it will affect the overall propagation. So that obstruction would cause diffraction, that we'll be discussing later inshallah in this week. But for the time being, you have to focus on that that we have a wave which is extending from this transmitter and receiver. So if you see that the different components of wave that would reach at the receiver side would have different phase difference in the phases. So there will be certain differences in the phases. So if I ask you to what is the difference of phase when the ray goes from a certain distance from this line of sight path. So there is a line of sight path here available here. If you see a wave covering a distance somewhere here, and you see it's reaching the receiver, in that case there will be a difference. If it's taking an even larger area, so it's coming from the longer path, in that case difference would get increased. So the different components of the wave would be received at the different distances. So what are the Fresnel zones? Fresnel zones are actually these imaginary lines. Actually there is no physical line here, they are imaginary lines. So they are showing that whenever the region where the direct path and the reflected path, they have a difference of phase of half wavelength or pi radians. Actually if you phase, you call in phase difference, so you will have a pi radian difference. So similarly the first Fresnel zone would have a difference of pi radians, second or lambda by 2 wavelength. The second Fresnel zone would have a difference of 2 lambda by 2 or 2 pi radians. Third Fresnel zone would have a difference of 3 lambda by 2 or 3 pi radians, and fourth Fresnel zone would have a difference of 4 pi or 4 lambda by 2. So different Fresnel zones, they corresponds to the length differences of n lambda by 2, where the transmitter and receivers, they are represented as the foci of this Fresnel zone. You can see that these Fresnel zones, they appear as ellipsoids, so they are elliptical in nature. So if any ray which is coming from the first Fresnel zone, then you can see that there would be a difference of lambda by 2 at the receiver side. So any ray which is coming from an odd numbered of Fresnel zone would cause a destructive interference, because as you say, odd number means 1, 3, so the difference is actually multiples of pi or 3 pi or 5 pi and so on. So these would represent that the two components of the rays which are received at the receiver side would be totally out of phase. So eventually they will cause destructive interference. And if the rays are coming from even numbered Fresnel zone, for example second Fresnel zone, so it will have a 2 pi radians, and 2 pi means the wave would also return back to the original form, so they will be in phase with the line of sight wave. So eventually they will cause a constructive interference. So all the odd numbered Fresnel zones, they represent the region where you have destructive interferences, and all the even numbered regions, they are representing the regions where you would see constructive interference. Generally the radius of each Fresnel zone, which is illustrated in the previous diagram here as well, the nth Fresnel zone, Rn is actually radius of nth Fresnel zone. So this nth radius is related to the distance between transmitter and receiver and the wavelength of the wave. So if you are observing the radius at this point, for example this P, which is at a distance of d1 from the transmitter and at a distance of d2 from the receiver, so at this point the radius of the Fresnel zone would be represented with this expression n lambda d1 d2 upon d1 plus d2. So d1 plus d2 is actually the total separation between transmitter and receiver. d1 is the distance from transmitter to the point of observation, and d2 is the distance of point of observation from the receiver, and Rn is the radius of nth Fresnel zone. N is integer. From this entire discussion, you should note that for wave propagation it's not sufficient to have a clear line of sight. Actually, not only the line of sight should be clear between transmitter and receiver, but also this bold line, this Fresnel zone region would also be cleared, because the region within that first Fresnel zone, especially because that has a significant contribution, the first Fresnel zone region, if it gets obstructed, even if there is a clear line of sight, it will cause losses in the propagation. So if there is an obstruction here which is not obstructing the line of sight, but still in the first Fresnel zone, it will cause losses. So it is important that at least the first Fresnel zone is clear and there is no obstruction in that first Fresnel zone. But for most of the practical cases, even if we have only 55% of the first Fresnel zone which is clear, so we get significant amount of the wave, and the loss related to this 55% clearance is very minimum. So if you have only 55%, more than 55% of first Fresnel zone cleared with obstructions, so we can get a significantly good amount of power at the receiver side without any loss. So after having discussion on the Fresnel zone, let us move our discussion towards the loss which is caused because of diffraction. So let me quickly recall what is diffraction. Diffraction is a important phenomena in wave propagation which refers to the bending of rays from sharp edges. So let's say if we have a mobile here and a base station here, and we have a building which has a sharp edge here, so even if there is no line of sight at this region, so any ray which is coming from closer to this sharp corner or edge of this building, so it will get bended. So you would see rays coming downward from this bending, this diffraction phenomena. So this diffraction phenomena cause generating secondary waves. Actually there are multiple wavelets which are generated when the wave gets hit by wave hits a sharp edge. So these secondary waves are important in the phenomena in the radio wave propagation because it allows us to receive the signal in the shadowed region here as well. You can see if a mobile is at this point, in that case there will be no line of sight path, but because of diffraction this mobile would also receive certain amount of power. So this diffraction, although it causes losses, but still it's useful because it helps spreading of the wave in the shadowed regions as well. So RF energy can propagate around curved surfaces from Earth because of diffraction, even if there is not a line of sight between the mobile, the transmitter and receiver. In that case you would be able to receive some signal. So through this diffraction we get the signal behind the obstructions as well. Through diffraction, although we get a reduced amount of power as compared to the line of sight, but still that diffracted field has sufficient strength of power, sufficient strength in order to produce a useful signal or establish the communication between transmitter and receiver. So this was the basic introduction regarding Fresnel zones and the diffraction. So we stop our discussion here, and we will continue this discussion in our next lecture in order to have a mathematical relationship related to the how much loss we would expect when we have diffraction between transmitter and receiver, or when we have any type of obstruction between transmitter and receiver. So we stop here right now. Thank you all.